In this problem, we will be ranking these molecules and to predict which is the more soluble in water. So we're talking the impact of intermolecular forces in solubility. And here I'm going to decide which of these is most soluble in water. So we're going to rank these molecules. For that, we are going to be analyzing what intermolecular forces we have and also the molar mass. Let's start with the how many carbons do I have here? This molecule has 1, 2, 3, 4, and 5 carbons. So if I am to name it, this molecule is pentanamine, that is 3,5 dihydroxy pentanamine, pent 4,5, right? Pentanamine. Okay, that's one. Number of carbons here is 1, 2, 3, 4, 5, 6. So I'm going to take note here. 6 carbons. Here I have 5 carbon. And this molecule is a diol. So it's 6 carbons. So it is 1, 4, hexane, diol. This is to say that I have 2 OHs and they are in carbon number 1 and in 4. Now here's the other molecule, and again we're going to count 1, 2, 3, 4, 5, 6, and 7. 7 carbon. No, this is also a diol, but it's hept, the prefix, so it's 2. Let's write it here. It is 2, 5, heptane. Oh, this is a P. Let's erase that. Heptane diol. Again, the di meaning we have 2 OHs, and they are in 1 and 5. Now, analyzing the number of carbons, this is 5, this is 6, this is 7. So the molar mass, I don't have it, I didn't calculate it, but it looks like this will be larger in longer carbon chains. So in regards to London dispersion forces, the longer the chain, the more London dispersion forces. But we will have this in all of the molecules. Now, how they interact with water is what matters when we're talking about solubility. Water, we know, is a polar molecule, and also we have a network of hydrogen bonding. This is in the liquid, and this is a dynamic process. Hydrogen bonds form and break continuously in the bulk. But when to analyze the solubility in water, I need to consider the enthalpy, the change in enthalpy, oscillation, and the changes in entropy for that process. Because now to dissolve in this molecule, for example, when I have this diol in just pure liquid, we will have, of course, London dispersion forces. We will have dipole, dipole, dipole. And I will also have hydrogen bonding. But this molecule is the largest, it's 7 carbon. When I analyze the molecule above, I have, again, always London dispersion forces, and I'm going to have dipole. Remember that here you have bonds that are polar. Let's draw the arrows. Here, here. So same on dipole, dipole. And I also have hydrogen bonding. But we see here that we have 5 carbons, so in regards to the mass. And here you have 3 polar groups in a smaller molecule. So say the hydrophilic part, it plays more important role. Whereas here we have more of hydrophobic. It still is polar, but again here this molecule is more hydrophilic. This, comparing this, for example, this two. So because we have fewer carbons, and more in, say, if we try to see how much it contributes, how much, say, the relative weight of the hydrophobic part and the hydrophilic part, here you have 3 polar groups and 5 carbons, so it's very likely to be soluble. And we can see this as when the solution happens, you're breaking interactions between these molecules and replacing those with new interactions. But this molecule is capable of compensate for the loss of hydrogen bonding between water molecules because it's replacing this with new hydrogen bonds. So again, the hydrophilic portion is weights more in this molecule than the hydrophobic portion because it has fewer carbons and it has 3 polar groups. This is 7 carbon, 2 polar groups. This molecule here is in between, so it has 6 carbons, so a little larger than that, in 2 polar groups. So again, the balance between hydrophobic and hydrophilic is what we are analyzing, and whether are we or are we not replacing these interactions with new interactions, solute, solvent, that need to be compensating for that to make this term favorable. And also in considering the entropy, whenever you're adding, in general, you're disturbing, they say solvent, adding other particles, although the solvent would reorganize around the solute, but there will be changes in entropy. So we need to see, in salt, for example, the entropy of mixing is typically favorable, so increase in entropy as we separate ions. More complex when we see organic molecules like that. But our main contribution to the delta G of solvation, so delta H minus T delta S, will be the enthalpy term. If we need to be thinking in replacing these interactions that were in the liquid with new interactions here that should be equivalent to overcome for that, so that in the end I have about the same type of interaction. And this is when the molecule is going to be most soluble. And this is like somewhat the principle of what you probably have heard, like dissolves like. We're simply saying that we're replacing, say, for example, this type of interaction with something similar between the solute that I'm trying to dissolve and the solvent. And here, since my solute has capability of doing hydrogen bonding, same as here, and the hydrophilic portion is more important relative to the hydrophobic because it has fewer carbons, so I'm likely compensating this interaction, so it should be favorable. Bottom line, if I'm gonna rank them as according to say solubility in water, the most soluble should be this. I'm gonna give it a number 1. So fewer carbons, more hydrophilic groups. And this one is follows, so I'm going to say number 2. This is 6 carbon, and here I had 3 polar groups, here I have 2. And this is the least soluble in water because I have more carbon. Here we have more. Here's 6, here's 7 in 2 polar groups. So that will be the least soluble of the 3 molecules.